back to track 1, computational pathology. It's my pleasure to introduce to the podium my colleague here at the University of Michigan, Mustafa Yousif, and also joining Elie de Brauwer, who's going to present their work in pathology QC solutions. And I'll let them further introduce what they've been doing. It's really quite impressive to see how the application of these technologies in the clinical pipeline now is coming of age. So welcome.
Thank you, Dr. Belize. Good morning, everyone. So today talk is gonna have, I don't have any disclosure, and Elie de Brauwer is an employee of Barco. So we're gonna go through past, present, and the future of this Barco QC solution that we co-developed together. And this is not an endorsement, but this is what we co-developed with Michigan, with the Barco team and Michigan Medicine. I'm gonna go through the past about the timeline, about digital pathology, transition to DigPath, the quality requirement, manual quality handling, and as well as the workflow of manual QC. This is just to give you an overview about the entire implementation. You might have seen this slide before, but this is just to iterate about when we started this entire project, it was 2021 when we started the first transformation proposal after that, and it took us almost 18 months to finalize the RFP, and we selected the image management system. So really the RFP, it's really time consuming. It can take at least of 6 months up to full more than a year. And then after that, it took us like every 6 to 7 months to move between each steps. For example, like after the approval, we have a budget approval and the IT endorsement. It took also about 6 to 7 months. And then after that, the hardware procurement and facility renovation, another 6 to 7 months. And then finally, the entire system integration and the hiring process and the entire FTEs for the manual QC. That was the main FTEs, as well as the project manager and the digital pathology and also the administrator to run the image management system. And finally, we went live around July 2024. And if you scale it really the right way, you will see that you can be on track. So for example, we divided our go live for the in-house of all the H&E and bright field, immunohistochemistry stains, special stains, all in-house services. We divided it into 5 stages. And as you see right now, we did also went with 2 go live time. The first go live was the technical go live, and it was intentional to go technical go live before the clinical go live because we want to make sure to stress test the entire system to see what if we figure out any issues with the system. So, and it was about like 4 to 6 weeks before we went live with the clinical production. And we also scale it out into the exact right services, right number of the faculty that we need to support each stage. And as you see right now, every kind of 3 to 4 months, we lay out those services. And we put also a hybrid workflow of providing the glass and digital distribution with, setting the mindset right now of saying that after that period of time, there will be no glass distribution. So that was set from the beginning, from the department, from the chair, from everyone. So everyone, already think that, okay, the glass slide might have it right now, but not anymore in the near future. And as you see right now, we just right now are going live with the stage 4. And then today we are on track on every single stage. And also for the first 2 stages, as you see right now, the chief services from peds, renal, autopsy, really everyone reached out and they say, I don't want to see glass anymore. Please, can you help us of not, archiving those slides right now? And we are right now building kind of a staging system because we need to put a staging area for those glides in case for fast retrieval. And after that, after the case is signed out, the case will be archived. This is just to give you a background about the number of slides that we are generating and the number of scanners that we have and vendors. So we have around like 2,500 to 3,000 slides per day. And mainly it's the bright field standard H&E, but we also have large microscopic slides, about like 20 to 40 slides per day. We also have immunoperoxidase, special stain, and slides for polarization, about 20 slides per day. Immunofluorescence, we also have immunofluorescence, about 40 slides per day, and our service is about 24/7 or 24/6. Like Sunday is like half a day. We have multiple scanners from multiple vendors. As you see right now, scanners for high throughput, scanners for immunofluorescence, scanners for manual scanning, because sometimes for those scanners at the time were not available for manual scanning, and also a scanner for polarization, and we also have for oil immersion if needed for higher magnification. All of those are generating a standard format, which is a DICOM format. And then this is what I want to also share with you is the workflow in pathology. The workflow is about, start from accessioning. So before we went live, or even before we started the entire project, we really studied the entire lab, and we divided it into 5 parts, which is, start with the accessioning, lab processing, and then we added this entire step. As you see, this is not intended to, read all the diagram, but I want to show you the ScanTech workflow. It's a huge workflow, and I'm going to go in details in these steps. So, and then after that, there's a case assortment, case distribution, and then faculty and trainee also kind of review or workflow. So, in order to really achieve a full digital transition, I think, in my opinion, there are multiple steps in order to achieve that full transition. So, for example, the first step is, the digital pathology workflow optimization, and it really starts from the accessioning when you receive the case. And definitely with grossing, make sure that, any single step, by the way, if you really want to do what's called PACS-driven or image management system-driven pathway, you have to make sure that these steps are tremendously important and on the right track. Otherwise, if, for example, your PA forget to finalize the case, they gross the case, they push the blocks and everything, but they forget to finalize. In the physical workflow, that is okay, that is not a problem. But in the digital workflow, anything you touch, you have to finalize in order to move to the next step. So embedding, same thing, when you embed all these tissue and the microtomy, sectioning of these, make sure the size of these tissue are within the acceptable tissue sections. And finally is the barcode. I can't emphasize how important to have really a good barcode printer to make sure that, in order when you start scanning, this is also a quality issue to make sure that, you don't have a lot of missing, for example, images because there's a failure in the barcode detection. And then I'm not going to go through the optimization, but definitely you need, to think about the optimization between your lab information system and image management system. And I want to focus on the slide scanning. As we said, high throughput scanning, definitely specialized scanning if you have, these type of polarization, immunofluorescence, etc. But today's talk is really, I want to focus on the quality control. And in my opinion, the quality control is the really important step in order to achieve this full digital transition. So, why QC check performed at this moment? So definitely we want to make sure that ensure diagnostic grade images for the pathologist. We want to protect patient safety by preventing error and caused by blur, misfocus, or missing tissue. We want also to reduce the cost of rescanning after, or the delay of those cases after distributing those cases, unfortunately. And then definitely meet the accreditation and the requirement. But the main issue, as you see right now, it's not really always easy for the scan technician, to review all these tissue, because what we really focus on our workflow is we want to make sure that there is no missing tissue, and this is CAP requirement. Every single tissue on the glass slide has to be interpreted. And the other thing is out of focus area. These are the main really focus in order to achieve a seamless workflow. There are a lot of artifacts, definitely pen mark, definitely microtomy tracks, things that maybe folds, but all of those really are, in my opinion, the only essential is the out of focus and tissue detection. And this is the workflow that I showed you, but in details, I'm going to focus only on two things. As you see, in the center is the all tissue detected. That's number one. And this is the main workflow on our scan technician, that they're going to go on every single slide or every single case that they digitize. And then the other thing is the all images were, in focus. As I said, we have 24/7 labor. We have 8 FTEs in order to manage the digital pathology workflow. All cases, which is in-house cases right now, was live, are being scanned 100% manually. And all slides are QC'd, including frozen section, H&E, and immunohistochemistry staining. The first step that I want to focus on is, missing tissue check. And it depends on the scanner vendor that you have or the image management system that you have. The missing tissue check right now, it's either we do it, right now we are doing manually, but Elie will show you the automated workflow. And either you have maybe a small screen on a scanner, or maybe a scanner have really another monitor that you review at tissue detection. What I'm saying about tissue detection is the tissue within this green box. Unfortunately, even sometimes this green box might not be provided, or the image management system cannot even display it, but the coordinate, this is a guideline, coordinate should be provided from the scanner vendor to the image management system, and then the image management system should display that green box, which everything should be within the green box. And as you see right now, our scan technician is really, every single slide that we scan, we review. We have on one of the scanners, the screen, and then they review the tissue, that all tissue detected within the green box. And then after that, they will take the rack or the tray and then move to the next step. The next step is to do the in focus, or to make sure there is no out of focus. And what we really realize, we have multiple issues that we witness: faint, control omitted, and the paucicellular slides. And for example, the tissue detection failure, mainly with those artifacts, as I'm showing to you right now, this is really faint or immunohistochemistry stain that sometimes not within the green box. The other bias is, sometimes it only focus on the positive tissue and then can omit area that, maybe control or maybe TMA. And then the final issue is really paucicellular issue. As you see right now, the tissue is really missed in that area. Handling those, we have to definitely do either like rescan the entire slide, and again, this is manual, so this is really time consuming, and all these, missing, blurry that you have to rescan it if there is a lot of percentage. The other issue or the other problem is you have to take that rack or that asset, that physical asset, and then you have to go to image management system. And not every image management system is really built the way that really kind of tech-oriented. Many of those image management system is really kind of directed to the pathologist or to the clinician. So it's like kind of patient-driven or case-driven. What you really need, you need kind of workflow to the technician so they can review the exact artifact or the exact slide. Maybe some of the image management system can provide this, but what I witness is like sometimes we really struggle with this. So what I'm trying to show you here, for example, this is only 3 slides, and then sometimes you see, although you get a column with like QC not done, for example, and maybe imagine if you have 100 slides and all of these slides in detail shown to you in one line. So it's really kind of time consuming to check every single case or every single slide. And then after we open the case, we do right now in our requirement, we scan the out of focus or in focus, the tissue at 10 magnification, almost like at least 4 to 5 regions of interest right now to cover all the area that is in focus, at least at 10x magnification. Sometimes we go to 20x magnifications, like for example with the renal biopsies, because it's really hard to detect at 10x, and this is really time consuming. And then the next step is we go to what we call the in focus. So to pass QC, again, maybe some of the image management system that can give you pass QC or fail QC. So for example, in this system, show you there is a check mark when we do manually that everything is like in focus. This is great. If there is anything in out of focus or there is anything like issue with it, we will reject. And this is a slide to show you that this is not rejected yet or no QC has been done. And then with that, I will right now let Elie to go through the present.
Thank you. Okay, so in the present situation, we're actually extending the manual QC and we're replacing it by an automated QC. In the first step, the automated QC, instead of the scan tech actually going through 100% of the slides, we add a QC solution. The QC solution will pick up the slides, run a set of AI algorithms, and only triage them into cases where there is a clear quality issue, or quality issue is present, quality issue is complete absent, meaning you have very well a good slide. Those cases will be automatically QC approved. In the case that we're really in doubt and the system is in doubt, the case will actually be forwarded to the scan tech. So the scan tech will only, instead of 100% of the cases, need to be bothered with roughly estimating 10% of the cases. This is a massive improvement in speed, lowers the throughput, and they only need to focus on the interesting things. Also, if they need to start examining the difficult cases, they will be guided by input by the AI. So we already have some idea on where we think issues are present, and they just need to verify and confirm this. Another important aspect of this is that at this moment, the slide can remain in the rack and the rack can remain in the scanner. That means that should there be an issue with the slide and it needs to be rescanned, the flow of material actually decreases, and you can do a more efficient rescan because you don't need to put the slide back in the rack and the rack back in the scanner. Looking one level deeper, what does such a quality control solution actually looks like? It all starts from the left. So we have a number of scanners. They all provide their WSIs into the VNA. And then in our solution, we have an input integration component. We actually receive a trigger. We consume the slide, and we provide the slide to an ensemble of machine learning models. Each of these models is focusing on one specific aspect, detecting a specific quality artifact, for example, missing tissue or a focused tissue. This is being aggregated into a complete quality control result that's being uploaded into central storage. For the difficult cases, we actually have the human in the loop to actually come to a verdict. For the simple cases, or the ones that are clearly okay or clearly not okay, we collect all the results and they can be automatically transmitted back via an output integration component back to the PACS or the IMS, meaning the checker mark that Mustafa just showed is set fully automatically in real time. Two additional things that I did not yet mention. We also have an anonymization component. If there is a disagreement between the human observer and the AI, we can actually consume the slide, anonymize it, send it back to the vendor, where it will be analyzed, annotated, and used for retraining of the algorithms. Furthermore, we also have a QC dashboard. The QC dashboard is actually a means to show the treasure trove of information related to all the quality that's happening in the lab that is actually presented, for example, to lab managers for decision making and for timelining and measurements. Next, I'm going to go a bit deeper in what such a solution actually practically looks like. First step is actually the main entry point for the Scantac. So this is the work list. Unlike a work list specifically for a pathologist that is case-oriented, this design has been made specifically for a Scantac. Perhaps not extremely well readable, but you can very easily say, okay, I want on scanner number 5, rack number 3, show me all these cases. You'll have a clear overview of the labels, the macro images, the overview images, some key parameters like the tissue type and the staining, but here also a summary of the issues that were actually found and identified. Next, there's an animation. We start from the AMS. At the bottom, there is no quality flag set. We go to the QC solution, and we can actually approve or reject the cases. So this is the human in the loop saying, I approve or I reject the case. In this case, we do 4 rejections. Automatically, the quality flag is synced back to the PACS. And after these 4 cases have been sent to the PACS, you open the case again, and you can see that these have been rejected. So this loop is automatically closed. Going further from the work list, so the Scantac-oriented work list, there is also a detailed view where they can do more thorough analysis of the actual issues. So for the 2 issues that Mustafa mentioned, 2 examples here, one related to missing tissue detection. So we have a enlarged view of the macro image. Outside, there is one piece of tissue that was actually missing. So there's a specific highlight which can be toggled for missing tissue detection. We also have autofocus tissue detection. In the past animation you saw, we already showed some contours where we suspect that the blurry areas are. But we also have like 5 sample points that we sample from the blurry regions to give an indication, okay, we think that at this point the most blurry areas are present. So they can simply confirm this by looking, okay, is it a fact or is it not a fact that these are the blurry areas? This gives them gives more concise steering to the Scantacs to give them some orientation on where to actually look for things. Some of these things sound trivial. They're not that trivial if you start to implement them. So I'm going to give some examples where it's particularly difficult for AI algorithms, but also difficult for humans. In this case, we're in the context of missing tissue detection. Assume for a moment that you're a machine learning algorithm and all you see is like squares that are like 200 by 200 pixels. So you see this and you need to identify this as being tissue or not tissue. We as humans, we like some context. So if we add some context, we can clearly see that number 1 was a fingerprint, number 2 was some staining residue, and number 3 was actually tissue that was present. The next challenge is in this case, which is quite poorly visible, unfortunately, but it was also poorly visible for the scanner, because in this case, it was actually a focus issue. The scanner tried to do some post-processing, applied some sharpening filter. The sharpening filter resulted in some poorly visible ringing artifacts. But because of the ringing artifacts, a naive implementation of an autofocus detection algorithm would actually identify this as being sharp while the tissue was actually quite blurry. Another example, which is a perfectly very well slide, this is this is a thyroid tissue where there is some colloid material inside the follicles, but there is like no structure, no edges. So any naive implementation would say this is blurry as hell. There are like no edges present. But if you would do this for all of these follicles, and you would have a threshold, for example, saying where you only allow 10% of tissue to be out of focus, okay, at that moment you would reject this perfect slide. So this is also something that needs to be taken into account when training these algorithms. Next, some examples where the human was actually wrong or where there was an issue at the area of the Scantac. Mustafa explained that on the Scantac, on the scanner, there's a display. We can look there for missing tissue. Here, the Scantac obviously missed some things which were identified by algorithms. Same for blur detection or autofocus detection, which also looks lovely, certainly from this angle. But the contours that you see These are the blur contours that were added by algorithms. The scan text, they take 5 random sample points. If they stay outside that area, they could conclude that the slide is actually quite sharp, while in theory, while in practice you see the highlighted areas, there are certainly areas that are affected by focus issues inside the scanner. Final part of the UI that I want to show or highlight is actually the dashboard that we are offering. So we collect a lot of data. This would allow us to have some insight on what is the throughput on the lab, what is the workload on the scan tags, how are the algorithms performing, how are artifacts actually evolving over time. This could, for example, allow you to identify if a certain scanner is misbehaving or requires some calibration. And this is something that we still plan to further exploit. Any takes on this?
Yeah. So I also want to emphasize that I'm really excited about this dashboard because I'll be honest with you, I was thinking, when I started this entire implementation, like, reach out to the scanner vendor and I requested, a dashboard. The issue is you're gonna struggle, like, because you have a dashboard from multiple vendors, like at least 3 to 4 dashboards if you are work with multiple vendors. And this one can work with any vendor as long as you have, the standard format. And this is not also gonna, help you to find these quality issues about the scanner, but also the quality issue of your entire lab. As you see right now in the top, you can filter it by the day, by the scanner, by the time, by the even stain type. So you can leverage those to kind of go through the quality of the lab and give feedback. Hopefully, maybe there is a tissue processing issue or tissue or a stainer issue at that time that we need to focus on. So dashboard is extremely powerful, and not also for this out of focus area or tissue detection, but the entire lab, even if you have label issue. I want to go also through the validation. The validation that we have done is we let the scan technician, 3 scan technicians, go through multiple slides, and they did manual scanning first. At the same time, the AI or the Barker QC was also run at the same time when there is a manual QC. And then the technician, after that, they do a comparison between the results of the AI plus the results of the manual. Either there is no quality issues or quality issues detected, and what are those quality issues. And so far, we have done in the validation more than 3,000 slides in the last 2 months of manual inspection of those slides with multiple technicians and more than 13 services, and also that includes bright field of immunohistochemistry stains as well as H&E. What's really interesting is when you go to the next slide is really what we found. It's really high sensitivity, high specificity of both missing tissue and out of focus area. When you compare it to the manual scanning for the scan technician, the sensitivity, as you see, is really right now low because really, as I said, we are limited of the quadrant or because it's very, very time consuming. That's number one. Also for tissue detection, because you have a small screen that you really make sure to go and make sure that all tissue has been detected. What we found that if we use the AI inspection, it can reduce like more than 90% of the time that the technician, and if you put that into account of 2,400 slides, you will get about like minimum of 40 seconds, and that translates into about like minimum of 11 or 12 to 24 hours per day shift, so this will definitely gonna save you an FTEs. And we also, what we found also, I didn't share this one on some slide, is there is also discrepancy between multiple technicians. So for example, first technician only took around 180 slides, like an hour and a half. The other one like took 4 hours. So there is also discrepancy of tissue detection, out of focus, and the AI will standardize all this workflow. Next, I'm gonna give future.
Okay, ending this part with some future work. So we started with missing tissue detection, focus and blur detection, because this was top priority for Michigan Medicine. We also have other algorithms in the cooker. For example, detection of marker, detection of faults, and tissue outside the cover slip. Also, we are building upon a roadmap, so if somebody has a strong opinion on which quality artifacts we should add, come visit us at the Barco booth. Happy to have a discussion on this. in terms of continuous improvement of AI, two important things to mention. I already mentioned in the initial diagram that if the Scantek disagrees with the AI, there is a possibility to close the data loop to actually quickly annotate what the actual issue is. Slide will be anonymized, will be shared back to the vendor, where we will be doing some analysis, some annotation, and some retraining on our side. But also as important is the algorithms that we deliver, they also need to be configurable at runtime. So based on the needs of the lab, based on the workflow that you're using, for example, are you doing a for diagnosis workflow or for archival workflow, you will have different requirements, you will have different settings and thresholds. The dashboard will help you to set these things, but this allows you to tune such a solution to your situation in the lab. Finally, ending with some shout-outs in the direction of DICOM. For missing tissue detection, some macro images and an overview and matching overview image. From a software vendor, if you start with proprietary image formats, and you need to detect if there's tissue present outside the area that was scanned. If you don't have the metadata, this becomes really painful. Here, okay, you can do some computer vision, you can do a green rectangle, you can do a detection for the green rectangle. Here you could try to fit this area into that image. And DICOM life becomes actually a lot more simpler because you simply have the coordinates, you have the offsets. It's just a matter of implementing this once, and this immediately applies to all the DICOM formats that you receive. Well, for the proprietary formats, for each of these things, we need to do custom development, custom integration. That's really a pain for a vendor. Some additional advantages as that when you can deal with DICOM, your development velocity goes up massively. Also, for example, a specific case that we have, we need to collect data that is also contains a macro image. On the macro image, the label is also present, depending on the contents and the placement of the label. Also, some private information, some undesired information can actually leak in. So what we're doing is we're masking this area out. This is very fun to do on DICOM. It does not take that much lines of code to implement. This becomes quite terrible if you need to do this on proprietary file formats. Libraries like OpenSlide, for example, they have accessors. You can read the files, but trying to serialize them becomes much more challenging, and you need to start doing it yourself at TIFF level, and you probably break break compatibility with existing viewers. In order to have a for Scantek worklist, you also need to have access to the metadata. That means that, for example, the acquisition context that contains a rec number, we need that metadata to be present. Unfortunately, not all metadata is filled in. So, for example, for the staining, there we're still using a proprietary API. Well, there's plenty of room in the DICOM standard. It's specified where it should be, but it's the integration with the LES that's not yet filling these fields properly. Also, some future work on our side. One of the reasons to also have these QC annotations, if you could serve these as inputs to, for example, clinical AI, you could have mask out regions. If you say, okay, it's a bad slide, we don't have that much tissue, but we know that this is actually the part of the tissue that actually should be going into an AI. If we can store those annotations, this could also be useful information to be passed along down the chain when we want to interface, for example, with clinical AI down the path. Finally.
So takeaway message, manual scanning is really time-consuming and labor-intensive. The QC automated really certify, each slide and lab quality is a benchmark. And then finally, I want to emphasize the, DICOM really accelerated development and support the flexible anonymization and enrich the QC metadata. With that, I'm going to thank you so much for the Barco team, as well as the Michigan Medicine team, Peter, Alette, Jonas, and Bart. And we are open to question right now.